This is Advanced Math 12.7 homework questions. That's Advanced Math, Unit 12, Lesson 7. I'm going over those four problems here, 4, 5, 6, and 10. Okay, starting with, and this is off of the worksheet from my website or from the packet, depending on how you're doing this. Number 4, a bacteria culture that doubles each hour has an initial population of 5,000 cells. How many cells are present after 42 hours? Leave your answer in exponential form. Okay, so I know on these, I'm going to use the formula y equals ab to the x. Now, on a test, when they don't give you the formula, notice they didn't give us a formula there. They went straight to how many cells are present after 42 hours. You have to make up the equation on your own. On numbers 1 and 2, and even 3, it walked you through it. Part A, come up with the equation. Part B, how much is left after so much time. It didn't do that here. It just went straight to the question, and that will happen on test. You have to know, hey, part A, I need to come up with the equation first. Part B, work it out. Okay, so even though there was not a part A and a part B, I need to come up with this equation first. I need to find my A and my B. X and Y will stay X and Y because they're variables. All right, so A is my initial amount. The number on this side is always the initial amount. And it says that the initial population is 5,000. And it doubles each hour and has initial population of 5,000. Okay, so after X is time, 1 hour, my ending should be 10,000. Okay, how did I get that? It didn't give that to us. I just know that because it says it doubles each hour. And because it doubles each hour, I know that after 1 hour I end up with 10,000. Now I can plug this in to find my B. B is what I am looking for right now so that I can come up with my equation because I already have A and all I need is B, and then X stays X and Y stays Y. Okay, Y is 10,000 equals 5,000 times B, we don't know, raised to the X, which is 1. I'm going to divide both sides by 5,000. B to the first power is 2. B to the first power is just B. B equals 2, which makes sense. B is my growth factor or decay factor. It's a growth factor because it's bigger than 1. And it's 2 because it's doubling. If it doubles in size every hour, the growth factor, the growth rate is 2. Okay, so my equation is y equals A, which is 5,000, is my initial amount, times 2 raised to the x power. Now, it did not ask for this equation, so this is not your final answer, but this would be in your workspace. Your final answer is going to be once you plug it in. Now, the question was, how much is left or how much is present after 42 hours? That's time. X is time. So X equals 42. Y equals 5,000 times 2 raised to the 42nd power. And it says to leave in exponential form, so this is what I'm going to leave my answer. If you actually plugged it in, it ends up being some really gigantic, huge, big number that it writes in scientific notation form, and it's just crazy big. So this is how we're going to leave our answer for number 4. Okay, number 5. Number 5 reads, this one's a little confusing. A certain container of water at 100 degrees Celsius cools in accordance with the formula T equals B plus A parentheses 2.72 close parentheses raised to the negative 0.03x, where B is the temperature in the surrounding air, A is the difference in the initial temperature of the water and air, and T is the Celsius temperature of the water after X minutes. If the temperature of the air is 22 degrees Celsius, what will the temperature of the water be after 15 minutes? Whew, a lot. Okay, I'm going to write down the formula they gave us so we don't have to figure one out on this one because it's given to us. All right, and then I'm going to write down what is what. It says B is the temperature in the surrounding air. And it goes on to say A is the difference in the initial temperature of the water and the air. I'm just going to put difference of temperatures between the water and air. And then what else does it give us? T is the Celsius temperature of water after X minutes. Temperature of water after X minutes. And minutes is the key part there as well. Okay, now let's see what was given and what we know, what we're looking for. Okay, if the temperature of the air is 22 degrees Celsius, temperature of the air is 22 degrees Celsius. If the temperature of the air is 22 degrees Celsius, what will the temperature of the water be after X minutes? This is what we're looking for here. So what is the difference in the temperature? Now, if you go back to the wording, it says A is the difference in the initial temperature of the water and the air. A is the difference in the initial temperature of the water and the air. Well, the water is 100 degrees Celsius and the air is, where is that at? 22 somewhere. 22 degrees Celsius, so you do 100, take away 22 to find what that is. A 100 take away 22 is 78, so this is 78 degrees. And now you're ready to plug everything in. T, that's what we're looking for, we don't know what it is, equals B, which is 22, plus A, which is 78, times 2.72 raised to the negative 0.03 times X. And X is what we are looking for. No, they gave us X. Let's read it. What will be after 15 minutes? So let me write that down over here. X is time in minutes, and it equals 15 in this case because they gave us, they're asking us what it is after 15 minutes. I'm just going to plug that in my calculator. 15 times negative 0.03. So I'm just going to rewrite it. T equals 22 plus 78 times 2.72 raised to the negative 0.45. That's only so it's easier to plug in later. Technically, you could plug this in right now the way it is. You just want to make sure you put parentheses around like that. If you don't, you're going to get it wrong. Okay, I will let you plug that in on your own. 22 plus 78, open parentheses, 2.72, close parentheses, exponent key, that negative decimal equals, and you're done. Again, you can plug it in if you have a scientific calculator. A newer one, if you have an older one, you do have to plug it in a little differently. But if you do have an older one, I'm sure you've figured it out by now. So you plug this in just as you see it, 22 plus 78, parentheses, decimal, close parentheses, exponent, negative 0.45 equals, check your answer on the back of the packet, and you are good to go. Okay, moving on. I am going to now move on to number 6. Okay. During surgery, a patient's circulatory system requires at least 50 milligrams of an anesthetic. The amount of anesthetic present T hours after 80 milligrams of anesthetic are administered is given by this following equation. A, how much of the anesthetic is present in the patient's circulatory system 30 minutes after the anesthetic is administered. Okay, so well, actually, let me write down the formula first. So this is another one we do not need to figure out what the formula is because it is given to us. And T is time. And A of T is the amount of the medication after a certain time. The amount after a certain time, the amount of the anesthetic. Okay, and T is in hours. T is time in hours. Okay. Alrighty, so part A. Asking us how much of the anesthetic is present in the patient's circulatory system after 30 minutes. Okay, so T is 30 minutes. Now, if it is in hours, then it's going to equal half an hour or 0.5 of an hour. And we just plug it in. A sub t is the amount after time t, not sub t, of t. A of t equals 80 times 0.727 raised to the 0.5. And that there is what you're going to plug into your calculator. So get your calculator out and get it ready to plug in. So I have 80 times 0.727, close parentheses, exponent 0.5. And we get 68.211. Now, it stated earlier, I believe, let's see what it said. During a surgery, patient circulatory system requires at least 50 milligrams of anesthetic. So after half an hour, the person still has enough anesthetic in their system to continue with the surgery. Now, that's why if you've ever had surgery or know someone who's gone into surgery or seen it on a movie, you'll see the anesthesiologist stays there during the surgery, and that's because they need to administer more of the anesthetics to continue with the surgery. So they are trained and they sit there and they keep track of all this stuff to figure out how long and when the patient needs more. Okay, part B is given, I'm going to put part B up here. Part B is asking how long to the nearest minute can the operation last if the patient does not receive an additional dosage of anesthetic. So if the anesthesiologist says, hey, I'm only going to give them one dose, you need to be done with the surgery within that amount of time, how much time does the surgeon have? Okay, so I'm going to use this formula. A of t, this formula, equals 80 times 0.727 raised to the t power, and it's asking us how much time do we have to complete the surgery if only one dose is given. Again, in the problem it says you need at least 50 milligrams to do the surgery. So how much time will it take for us to reach the amount of 50 is what it's asking. How much time do we have before we reach 50? So I'm going to divide both sides by 80. So plug that in your calculator, 50 divided by 80, and you get 0.625 equals 0.727 raised to the t power. Change to logarithmic form and then use your change of base, or the way I've shown you in class or in notes is take log of both sides, not multiply by log, but take log of both sides. And we do that so we can bring the power of t down. Using our log laws, an exponent comes down as a coefficient. So I have log of 0.625 equals t times log of 0.727. And then I'm going to divide both sides by that log to get t by itself. Log of 0.727. And this right here is what I'm going to plug in my calculator to get t by itself. Okay, so let's get our calculators ready. And I am going to plug it in. What was it? Log of 0.625. Don't forget to close your parentheses. Divide log of 0.727, close your parentheses, that one's not necessary, equals 1.474 hours. So almost 1.5, so quite about almost 1.5 hours before they would have to have the surgery complete. So time equals 1.74 or 474 hours. So a little under, smidge under an hour and a half. Okay. Part C to the nearest minute, what is the half-life of this anesthetic? Remember, half-life is the amount of time it takes for you to end up with half of what you started. A of t is your ending amount, so you're looking for the amount of time it takes for us to end up with half of what we started. We started with 80. That's the starting amount. And when you read the problem, it actually says that the amount of anesthetic present t hours after 80 milligrams of anesthetic are administered. So 80 is the initial amount given. How much time does it take for us to end up with half of what we started with? So half is 40. So 40 equals 80 times 0.727 raised to the t power. And t is what we are looking for. So divide both sides by the 80. And we end up with half, or 0.5. I'm going to continue it here. 0.5 equals 0.727 raised to the t power. Now, I am going to let you finish that part on your own. What you're going to do is take the log, just like we did over here. Take the log of both sides, bring the t down, and then log of 0.5 divided by log of 0.727. And that's going to be the amount of time it takes for you to end up with half of what you started with. And check your answer to the answer key. Part D says, pharmacists and anesthesiologists multiply a medication's half-life by 5 to estimate when a medication is cleared from a patient's bloodstream. To the nearest minute, how long does it take a patient to eliminate all of the anesthetic? So they multiply the half-life by 5. So what you're going to do is take 5 times your answer from here. Once you get that done and you get your answer, that's what you're going to plug in there. 5 times your answer from part C. So if you ever look at medication, especially heavy medication, it says cannot operate heavy machinery or required a driver after, for so much amount of time you should not be driving. This is how they calculate it. You should not be driving or operating heavy machinery for 2 hours or 3 hours. Whatever it is, they calculate it using this type of math here. Okay? And next one is number 10. Log of E equals 1.4 plus 1.5 R, and it says the energy E ergs released during an earthquake of magnitude R is given by this formula. Solve for E in terms of R. Okay, so that's all we're doing first, is just solving. Now, I want to get E by itself. Is there a log on both sides? There is not, so I cannot drop the log, which means I'm going to do a wraparound. 10 raised to all of that equals the E, and that's pretty much it. 10 raised to the 1.4 plus 1.5 R equals E, and you got E by itself. Part B asked you to find the energy released during the famous Alaskan earthquake of 1964, which measured 8.4 on the Richter scale. So for R, you're going to plug in 8.4, and you're looking for E. How much energy was released during that earthquake? And you're pretty much, you can plug it into either one. I'm going to plug it into this one since I already have E by itself, and E is what I'm looking for. E equals 10 raised to the 1.4 plus 1.5 times R, which was an 8.4 on the Richter scale. And you just plug that in your calculator. Because it does come out to be a big number, actually just plug it in and check it to the answer on your answer key, and you'll see how it works. Alrighty, that is it for this section of homework questions.